How Richard Feynman dismantled the clock of the universe and changed physics forever. Watch a beam of light pass through a piece of glass. It enters at an angle, bends as it crosses into the glass, travels straight through the interior, then bends again as it exits back into air. The path is predictable, precise. You can calculate exactly where the light will go. But here's a question that sounds strange. How does the light know to take that particular path? How does it know at the instant it hits the surface what angle to bend to, given that the fastest route through the glass depends on the thickness of the glass, the angle of entry, and the properties of the material? Classical physics has an answer. Light follows the path of least time. It takes the route that minimizes the total travel duration. This is Fermat's principle, known for centuries. But that answer just pushes the mystery back one step. How does light compute all possible paths and select the optimal one? Does it try them all in advance? Does nature solve an optimization problem at every boundary? Richard Feynman had a radically different answer, one that overturned the very foundation of how we think about particles, forces, and time itself. Light doesn't choose a path. Light doesn't follow a route. Instead, every possible path contributes to what happens. The paths interfere with each other, like overlapping waves. Most paths cancel out. A few paths, clustered near what we call the optimal route, reinforce each other. What looks like a choice is actually the result of quantum interference across all possibilities simultaneously. This insight didn't just explain light. It became the foundation for quantum electrodynamics, our most precise theory of nature. And it forced physicists to abandon the idea of a clockwork universe running on predetermined tracks. Let's see how Feynman dismantled that clock. Least action emerging from interference. To understand Feynman's breakthrough, we need to think about waves and interference. Imagine you're standing in a field during a windstorm, holding a compass. The needle spins wildly, never settling on a direction. North, east, south, west. The chaos averages out to nothing. No net direction emerges. Now imagine the wind starts to calm in one particular direction. Most gusts are still random, but there's a slight bias. Gusts from the north happen more often and last longer. The compass needle still fluctuates, but it spends more time pointing north. A pattern emerges from the chaos. This is analogous to what happens with quantum amplitudes. Every possible path a particle could take between 2 points contributes a quantum amplitude. An amplitude is like a compass needle, a mathematical object with magnitude and direction. But instead of pointing in space, it points in an abstract phase space. You can think of each path as contributing a rotating pointer. As the particle travels along that path, the pointer rotates at a rate determined by the action along that path. Action is a quantity from classical mechanics, roughly the difference between kinetic and potential energy accumulated over time. For most paths, the action varies wildly. A path that takes a huge detour has different action than a path that zigzags back and forth. These paths contribute pointers that point in completely different directions. When you add them all up, when you sum over all possible histories, most of these pointers cancel each other out. One points north, another south. One points east, another west. They interfere destructively, like waves that are out of phase. But near certain special paths, something different happens. Paths that are close to the path of least action have similar amounts of action. Their pointers all point in roughly the same direction. They're in phase. They reinforce each other. This is why classical mechanics works. It's not that particles actually follow the path of least action. It's that paths near the least action path constructively interfere, while all other paths destructively interfere. The classical trajectory emerges as the dominant contribution from quantum interference. Feynman realized this in the 1940s, building on earlier work by Paul Dirac. But Feynman developed it into a complete framework for doing calculations. He called it the path integral formulation of quantum mechanics, and it changed everything. Path integral explanation. The path integral is a strange and beautiful idea. In classical physics, a particle moves from point A at time 1 to point B at time 2 by following a single definite trajectory. You can track it. You can say where it is at each moment in between. In standard quantum mechanics, particles have wave functions. The wave function evolves according to Schrödinger's equation. You can calculate probabilities for measurements, but you can't visualize a particle moving along a path. Feynman's approach is different. He said, consider every possible path the particle could take from A to B. Straight lines, curved paths, paths that loop back on themselves, paths that zigzag wildly, paths that go halfway to the moon before returning. Every conceivable trajectory, no matter how absurd. Each path gets assigned a complex number, a quantum amplitude. The amplitude depends on the action along that path. Paths with larger action contribute amplitudes with faster rotating phases. To find the probability amplitude for the particle to go from A to B, you sum all these contributions. You add up the amplitudes from every single path. This sounds insane. There are infinitely many paths. How could you possibly sum them all? The mathematical answer involves functional integrals and careful limits, which we won't dive into. But the conceptual point is clear. You're not saying the particle takes all paths. You're saying all paths contribute to the amplitude, and the amplitude determines what you'll measure. In the limit where quantum effects are small, where the action is much larger than Planck's constant, the interference becomes extremely rapid away from the classical path. Only a narrow bundle of paths near the classical trajectory contributes significantly. You recover classical physics as an approximation. But when quantum effects matter, when the action is comparable to Planck's constant, many paths contribute. The particle doesn't have a definite trajectory. It's spread out over a range of possibilities. This isn't metaphorical. This is how quantum mechanics calculates probabilities, and it works. The predictions match experiments to extraordinary precision. Feynman's path integral formulation is mathematically equivalent to Schrödinger's wave equation. They're two ways of describing the same physics. But the path integral gives you a different intuition. It emphasizes histories and interference rather than waves and evolution. And for certain problems, especially in quantum field theory, the path integral is much more powerful. QED and diagrams. In the 1930s and 40s, physicists were struggling with quantum electrodynamics, the theory of how light and matter interact. The basic idea was clear. Electrons are quantum particles. Photons are quantum particles. They interact by exchanging energy and momentum. You should be able to calculate how an electron scatters off a photon, or how an electron emits light. But when physicists tried to compute these processes precisely, they kept getting infinities. Nonsensical results. The mathematics broke down. The problem was that quantum field theory allows for virtual particles. An electron can briefly emit a photon and reabsorb it. That photon can briefly split into an electron-positron pair, which then annihilate. These intermediate processes, invisible to direct measurement, contribute to the overall amplitude. And there are infinitely many such processes. An electron can emit and reabsorb any number of virtual photons. The calculations diverged. Feynman's path integral approach provided a new way to organize these calculations. He developed a diagrammatic method, now called Feynman diagrams, where each line represents a particle propagating and each vertex represents an interaction. You draw all possible diagrams that connect your initial state to your final state. Each diagram corresponds to a contribution to the amplitude. You calculate the amplitude for each diagram, sum them up, and get your answer. The diagrams are not pictures of what's literally happening. They're calculational tools, bookkeeping devices for tracking contributions to the path integral. But they also revealed structure Certain infinities could be absorbed into the definitions of the electron's mass and charge. This process, called renormalization, was deeply mysterious at first. It seemed like mathematical trickery, but Feynman's framework made it systematic. The infinities arise from high-energy virtual processes. You can isolate them, redefine your parameters to account for them, and make finite predictions for measurable quantities. Quantum electrodynamics became a predictive theory, and it's the most accurate theory in the history of physics. Some QED predictions match experiments to 10 decimal places. Feynman shared the Nobel Prize in 1965 for this work, along with Julian Schwinger and Shinichiro Tomonaga, who developed equivalent but different approaches. But Feynman's path integral and diagram methods became the standard tools for particle physics. Antimatter and time direction. There's a strange detail hidden in Feynman diagrams that's worth understanding carefully. In quantum field theory, every particle has an antiparticle. An electron has a positron. A quark has an antiquark. When a particle and its antiparticle meet, they can annihilate, converting their mass into energy. Feynman noticed something elegant in his diagrams. You can represent an antiparticle as a particle moving backward in time. This is a mathematical statement, not a physical claim about time travel. Let me be precise. Imagine a process where an electron and positron collide and annihilate, producing two photons. In the diagram, you have two electron lines coming in, meeting at a vertex, and two photon lines going out. Now, you can redraw this. Take the positron line and flip its direction. Instead of a positron moving forward in time toward the vertex, draw an electron moving backward in time away from the vertex. Mathematically, these descriptions are equivalent. They give the same amplitude, the same prediction. The antiparticle moving forward in time is indistinguishable from the particle moving backward in time. This is not science fiction. This does not mean you can send messages to the past or create paradoxes. The equations are time-symmetric at the microscopic level, but that doesn't translate to macroscopic reversibility. What it means is that the distinction between particles and antiparticles is subtle. They're related by symmetry. And Feynman's framework makes this symmetry explicit. Some physicists have speculated about whether all electrons in the universe could be manifestations of a single electron zigzagging back and forth through time. It's a beautiful idea, but it doesn't match observations. We see far more electrons than positrons in the universe. The point isn't that time reversal is real in a literal sense. The point is that the microscopic laws of physics are largely time-symmetric. The equations work equally well, running forward or backward. So why does time feel one way? Why do we remember the past but not the future? Why do eggs break but never spontaneously reassemble? That's a different question. Arrow of time. The microscopic laws of physics are time reversible. If you watch a film of two particles colliding at the quantum level, you can't tell if it's running forward or backward. Both directions are allowed. But the macroscopic world is not time reversible. If you watch a film of a glass shattering, you immediately know which direction is forward. This asymmetry comes from statistics and entropy. Entropy is a measure of disorder, or more precisely, the number of microscopic states that correspond to the same macroscopic appearance. A broken glass has high entropy because there are many ways to arrange the shards. An intact glass has low entropy because the pieces must be precisely assembled. The second law of thermodynamics says that entropy tends to increase over time in a closed system. This isn't a fundamental law like conservation of energy. It's a statistical statement. There are vastly more high entropy states than low entropy states, so systems tend to evolve toward disorder. This is why time feels one way. The past was lower entropy. The future will be higher entropy. And we, as complex structures embedded in this flow, perceive time moving from past to future. But at the level of individual particles, the equations don't care about the arrow of time. An electron scattering off a photon is time-symmetric. The asymmetry emerges when you have huge numbers of particles and statistical behavior dominates. Feynman's framework doesn't solve the arrow of time problem. That's not what it's for. But it clarifies where the asymmetry is and isn't. The microscopic rules are symmetric. The macroscopic patterns are not. And understanding this distinction is essential for thinking clearly about time, causality, and the nature of physical law. So what did Feynman really change? He changed how we think about what's fundamental. Before Feynman, physics was built on the idea of particles following trajectories. You specify initial conditions, apply forces, and calculate where the particle goes. The universe was a clockwork, deterministic, trackable. Feynman showed that this is an approximation, an emergent description that works when quantum effects average out. The deeper reality is interference, amplitudes, superpositions of possibilities. The particle doesn't follow a path. It explores all paths. And what we measure is the result of those explorations interfering with each other. This doesn't make physics less precise. Quantum mechanics is the most precise theory we have. But it changes the picture. It changes what we imagine is happening beneath the surface of the equations. The clockwork universe was comforting. It was intuitive. You could visualize gears and trajectories and causes leading to effects. The quantum universe is stranger. It's a universe where the future is not determined by a single thread of history, but by the interference of infinitely many potential histories, where particles and antiparticles are related by time symmetry, where the classical world emerges from quantum chaos through the delicate balance of constructive interference. Feynman didn't invent quantum mechanics, but he gave us a new language for thinking about it, a language that's proven indispensable for particle physics, for understanding fundamental forces, for building the standard model that describes nearly everything we can measure. And he did it with clarity, with diagrams, with a refusal to accept mystery when there was mathematics to be done. The clock of the universe didn't stop, but Feynman showed us it wasn't ticking the way we thought. So here's the question I'll leave you with. If every possible history contributes to the present, if the classical world is just the peak of an interference pattern, then what does it mean to say something happened? What does it mean to choose? What does it mean for there to be one actual history when the mathematics says all histories participate? Think about that. The universe is more subtle than we imagine, and that subtlety is worth understanding.